So now we'll consider some examples. So first thing we'll consider is an elliptical cross section. So just draw this x, y. And this is A. Equation of this is x square by a square plus y square by b square is equal to 1. And okay, so we want to solve this particular problem, and let us imagine that the load is P. So remember that this P is the resultant of the tractions that is being applied on this particular cross section. It is not a point load, but basically there is the resultant is only in the x direction. There is no resultant in the y direction, and we want to find out what is the stress distribution in this beam due to this load P. So according to our notation, we have Wx is equal to P and Wy is equal to 0 in this particular case here, and you can see that this cross section is doubly symmetric, so you will get that Ixy is equal to 0 in this particular case here, because the x and y will be the principal axis in this for this particular cross section here. So you will get that so since Ixy is equal to 0, you will get that kappa x is equal to, so kappa x is equal to P divided by E times Iyy. So go back to the formula for kappa x and kappa y that I had derived in the first lecture in this particular topic, and this is equal to 4p divided by E pi a cube b. So I have carried out this integration. Iyy is nothing but integral of x square dA. So I have integrated it over the cross section of the ellipse, and then I have got this a cube b by 4 as the value for Iyy, and I am substituting that into this one. Then similarly we will get that kappa y is equal to 0 in this particular case. Okay, then so then if you go now to this particular equation, you will see that this dx by ds is not going to be 0, right? Because dx by ds is continuously varying on this particular cross section. So if kappa y is 0, then g of x is also 0 from this, because we are satisfying these two conditions on the cross section. So if this is 0, then this also has to be equal to 0 here. So you will get that g of x is equal to 0. Yes, so g of x is equal to 0, and then in this particular case, the shear center lies at the centroid itself. Shear center lies at the centroid. That is because it is doubly symmetric. So we discussed this, that basically it will lie along the shear center always lies along the symmetry axis. So in this case, it will lie at the intersection of the symmetry axis. So here that is just going to be at the centroid itself. And then because the load is passing through the shear center, you will get that the twisting is 0. So in this particular case, since P is along the x-axis, see P acts along the x-axis, okay. Hence the twisting is equal to 0. Twisting is equal to 0. So that means alpha equal to 0. So that is what we get. And okay, then we go now to this particular equation here. Then from this equation you will get that f of y should be equal to, so f of y is equal to p times x square divided by 2Iyy on c. So many students, they will ask this difficulty. So let us just consider this. So here I am writing f of y, but here I am having an x. So students ask this difficulty, how can you have an f of y which is this, but this is important. On c, That is only on the contour this is true, not this is not everywhere. Okay, so on that contour your f of y should be equal to this px square. So there is a constraint between x and y in this on the contour, and so that once you substitute that constraint, you will get that f of y is a function of y alone. So that's why. So on C, so the equation for C is x square by a square plus y square by b square equal to 1, right? So you will get that. So f of y will be equal to p divided by 2 I by y times a square by b square times b square minus y square. Okay, so if you choose now your f of y to be this particular function, then you will see that it satisfies this particular condition when x square plus y square. So simply substitute, simply substitute for x square from this particular expression, you will get this expression. So automatically you will see that this equation is satisfied on that particular boundary here. Okay, now so after we get g of x, so g of x is 0, f of y is given by this. Now you substitute it into this particular expression here. So kappa x is known, kappa y is known, then substitute it here. So what you will get now, so let me call this as star. So from star you will get, so from star you will get that del square phi is equal to p divided by I y y times nu divided by 1 plus nu plus a square by b square times y. So this is what you will get as the equation for del square phi. And now we have to solve this. So now since both these conditions we are satisfied on C, hence we know that phi should be equal to 0 on C. So again, just if you recall in the case of torsion, we had a similar situation that del square phi was minus 2g alpha and phi was equal to 0 on the boundary there. So this is a similar situation, except that now there is a y here. So in the case of the torsion problem, the del square phi was a constant. In this case it is not a constant, it is dependent on y. So we have to modify our solution strategy a little bit to account for that presence of that y here. So now let us take what we will do is that let phi be equal to m times x square by a square plus y square by b square minus 1 times y. So then this we keep this y here because, as I said, that it is no longer a constant. So in the torsion problem we did not have this y here, we just guessed it as m times this. So now you can see that because the equation of the boundary is incorporated in this guess for phi, automatically phi equal to 0 is satisfied on the boundary here. And now you can substitute it into this particular governing equation and find out what is this m. Okay, so from that particular equation you will get that let us write that you will get that phi. Substitute into double star now, where this double star is this particular equation. This is now double star. So if you substitute it into double star, then you will get the value of m from that. Then the final solution. So final solution I will write phi is equal to a square into 1 plus nu times a square plus nu times b square times p y divided by 2 into 1 plus nu times 3a square plus b square times I y times x square by a square plus y square by b square minus 1. Okay, so this is what you will get as the final expression here. And then from this now you can get the expressions for tau xz and tau yz. Okay, so that is those formulae whatever I have given in the last class. So you use that in terms of the del phi by del x and del phi by del y. So you can find out what is the stress distribution. So you get that tau xz is equal to 2p divided by pi a cube b times 2 into 1 plus mu times a square plus b square divided by 1 plus mu times 3a square plus b square times a square minus x square minus 1 minus 2 nu times a square y square divided by 2 into 1 plus mu times a square plus b square. So this is the expression for tau xz, and then tau yz also you can get. So that is minus 4p divided by pi a cube b times 1 plus mu times a square plus mu times b square divided by 1 plus mu times 3a square plus b square times xy, and tau zz will be equal to minus 4p divided by pi a cube b times L minus z times x. So these are the expressions for the stresses. Okay, so that basically solves the problem, and then we can substitute all of this into the strain displacement. So find the strains, and then from the strain displacement you can find out the displacement field as well. So that we can do. But right now let me just note what are the special cases of this particular solution here. So so basically what we have to remember is that the so the traction distribution on this particular phase should be applied exactly in this particular manner. So you have to apply a tau xz in this particular direction, which is of this particular form, and you have to apply a tau yz, which will be here like this. So this tau yz has to be applied according to this particular equation on this particular cross section. Only then will this be an exact solution. So again, in an actual situation we will not be able to apply the traction according to this distribution. Then we have to use that Savena principle, that basically the we are getting a resultant load P through a different traction distribution. Then make use of this Savena principle, that away from the area of loading the solution will be almost the same here. Yes, so let us now look at what is the stress distribution along this particular axis, and so on and so forth. So let us look at some special cases here now. So I will get now that tau xz, so on the line x equal to 0 now. So that is the y-axis. Okay, so here I am trying to find out what is the distribution of stress along this particular line here. So you will get that tau yz is equal to 0 there. So tau yz is equal to 0, and your tau xz, so that is on tau xz at x equal to 0 is equal to 2p divided by pi a cube b times 2 into 1 plus mu times a square plus b square divided by 1 plus mu times 3a square plus b square. So this is times a square minus 1 minus 2 nu times a square y square divided by 2 into 1 plus mu times a square plus b square. So this is the this one, and so it has a maximum value at y equal to 0. So basically at the origin here you will get the maximum value here. So this is the tau xz max. So this is at x equal to y equal to 0. That maximum value will be equal to 2p divided by a this A is the pi AB, so that A is pi AB is the area of the ellipse here, and this is times 2 into 1 plus mu times A square plus B square divided by 3 1 plus mu times 3A square plus B square. So that is the expression for the maximum shear stress along that particular line. Then what about tau yz max? Okay, so let us now find what is tau yz max. This particular portion here. So in order to find tau yz max, we need to find what is xy max. Okay, so to find tau yz max, need to find xy max, right? And so that is not very trivial, but if you put x is equal to, so we will use a trick here. So you write x is equal to a cos theta, and y is equal to b sin theta, and then you will get that xy max is equal to half of AB sine 2 theta max. Okay, and maximum of any angle theta can be only sine theta, the maximum sine of any angle will be plus 1. So this is equal to AB by 2. Okay, so we do not know exactly where it is occurring along this particular boundary here, but we know that xy max is AB by 2. So if you substitute that, then what we will get is that, so let me erase this also. Now the tau yz max, you will get tau yz max is equal to 2p divided by a times 1 plus mu times a square b plus mu b cube divided by 3 a cube plus a b square. So this is the expression that you will get for this one here. So I mean, the reason for writing all of these expressions is that now you will see certain features that are different from the solution that you studied in your strength of materials courses. Okay, so here if you see that for B much greater than A, so for B much greater than A, your tau yz is not negligible. Tau yz is not negligible. Okay, so that means what is this B much greater than A means your cross section will look something like this. I am just drawing it here. Okay, so this is the case where B and this is A. So you can see that when B is much greater than A, so their tau yz is in this particular direction. Okay. See so what we are doing is in your strength of materials courses, we completely ignored tau yz. We said tau yz is 0, correct? And then we just took tau xz as the only stress component. So if you recall, your tau xz we would write as tau xz. So this is according to your strength of material. So SOM is standing for strength of material. So that, if you recall, that is VQ by IB, right? And A is that moment of inertia of a section above the particular axis, right? So that using this VQ by IB, we can, so we cut it here and then we will find out that integral of YdA. So that is this Q. So if you recall from your strength of materials courses. So what we were doing in the strength of materials is that we were taking, so suppose if there is a load P in this particular direction, we were saying only that the tau xz is the only non-zero component and tau yz is 0. But now what we can see is that if your cross section is very wide, like in this particular direction, then that is not a good assumption. Whatever you learned in your strength of materials is not a good assumption when B is much greater than A. But if B is much smaller than A, then actually it is a good assumption, right? Whatever was assumed in your strength of materials courses, that is a good assumption in that particular case here. So basically, to summarize, if you have this particular case and if you use your strength of material solution, then you can get very large errors, right? So you have to be very careful. So so suppose if your cross section is of this particular kind, like this, right? So this, then here it is okay, here it is not okay. So you use your strength of materials approximation, but for this case, you are okay to use the strength of materials solution in this particular case here. So that is why I am saying that that is the reason that I wrote all these expressions, so that you can see that for b much greater than a, tau by z is not a negligible quantity here. Fine. So let me just write that over here. So solution can give large errors, right? Your SOM solution can give large errors in that particular case here. Okay, now let us look at the circular cylinder, right? So circular cylinder is just a special case when A is equal to B, right? So you just set A equal to B, then you will get it. So let us do that now. So circular cross section. So in that particular case, you will get that A is equal to B. And then you will get that tau xz at x equal to 0 is equal to 3 plus 2 nu times P divided by 2 pi a to the 4 times 1 plus nu times a square minus 1 minus 2 nu times y square divided by 3 plus 2 nu. So these are again all exact results. So tau xz max, so that occurs at the center of the circle. So tau xz max is equal to 3 plus 2 nu times p divided by 2 into 1 plus nu times a. And your tau yz max, max is equal to 1 plus 2 nu divided by this particular thing here. So tau yz max will be 2 into 1 plus mu times p divided by 3 in this particular case here. Okay, so let's see. So okay, so if you now look at your strength of material solution, so SOM solution, strength of materials solution. So if you recall, then we will get this parabolic type distribution, because that through that formula VQ by IP we will get that parabolic distribution there, and then you will get that the maximum shear stress will occur at along the center line, correct? So basically if you draw this cross section, then the shear stress distribution is of this kind, and then at the center you will get the maximum shear distribution. So here, according to your SOM solution, strength of material solution, you will get tau xz max. So that is at the center here. That according to that VQ by IV formula, you will get 4p by 3. Okay, so now let us compare what we get from the exact theory and what we get from the strength of material solution here. So you will get that tau xz max. So this is now from the exact solution, exact divided by tau xz max from your SOM solution. So that is SOM, strength of material solution. So you will get that this is equal to 3 into 3 plus 2 nu divided by 8 into 1 plus nu. Okay, so this is the result that you will get. So if it is close to 1, then you are fine, correct? But if you are very far from 1, then there is a problem, correct? But here you will see that for nu equal to 0.3, the error is only 0.4%. Error is equal to 4%. That's all. So even for a circular cross section, your strength of materials assumption is a good approximation. But only, as I said, that only if you go to these kind of cases, then the strength of material solution will fail. But otherwise, the strength of material solution is a good approximation for cases like of this type, or even for a circular cross section also. It looks like it is a good approximation. But the thing to remember is that in the strength of materials, we are completely neglecting this tau yz component, right? And then here, actually we see that tau yz is not 0. So even if you are applying a load in this particular direction, it generates shear stresses in this particular direction also, right? And so that is important, and that we see in the exact solution. Whereas in the strength of materials, we say that if the load is in this direction, shear stress is also only in this direction, and there is no shear stress in this direction. So that is not correct, and strictly speaking that is not correct. But we have seen now how to obtain the correct stress distribution from this particular theory. Okay, so this example of an ellipse I have solved using the phi approach. That phi is this stress function. But we can also solve it using the chi. In the last class I mentioned that you can use that chi function. So in this, for this elliptical case, your chi will be of the form of c1x plus c2 times x cube minus 3xy squared. Okay. So you can see that this is a harmonic function. Harmonic. So that means your del square of chi is equal to 0. So this combination will satisfy the governing equation for chi, and then this C1 and C2 are to be found from the boundary condition, right? So this C1, C2, you basically now find out what is tau xz, tau yz from this, and then use the fact that tau xz nx plus tau yz ny is equal to 0 on the boundary, correct? So this is the C1, C2 to be found from tau xz nx plus tau yz ny is equal to 0. So and the normal will be given by, so suppose the equation on the boundary is phi equal to not phi, let us put beta equal to 0. So that is this particular equation. Then del beta divided by norm beta, del beta will give me the unit normal at a given point. So you can try to find it out. Actually, you need not divide it by this normalization factor, because on the right hand side you have 0. So you can multiply the whole thing by the norm of that beta. But you can try this out, and try to find this C1, C2 in this particular case by using this boundary condition here. So that is an exercise that I will leave it to you to figure out. Fine. So we will move to the next example, which is let's see. So yeah. So in one of your assignments, you have been asked to solve the case of an equilateral triangle, but I will just mention. So again, there also this phi approach is used for the equilateral triangle, but I will give you the chi function even for that one also, so that you can try it out on your own here. So in the so for the equilateral triangle, let me just write what the chi function is. this is an equilateral triangle cross section, you will get that chi is equal to A times kappa x by 9 times 2a minus 3y. So again you will see that this is a harmonic function, and you can verify that this function will satisfy the boundary conditions. So again, this is using the free approach that is given in your homework assignment. You can try out this chi function also, that it works here. Okay, so now let us look at the rectangular cross section now. So this is a very, very interesting case. So this is a rectangular cross section. So let me draw that here. Okay, so in this particular case, you will get that now Wx is equal to P. Again, just like for the elliptical case, we have Wx equal to P, and Wy is equal to 0. And then from this, you will get that kappa y is equal to 0 because Ixy is 0. So since Ixy is equal to 0, again x and y are principal axis in this particular case. So you will get that Ixy is equal to 0. And you will get that because kappa y is 0 and dx by ds is not 0 on the entire contour, so you will get that g of x is equal to 0. So this you will take, so this will imply that g of x is equal to 0 because on C you want to satisfy this particular condition here. And then now actually the f of y is quite an interesting case here. So this f of y, now you can take it as e times kappa x times a square divided by a. So that is equal because you can see that on this particular edge here, right, your dx by ds is not a constant, correct? On this particular edge, we are saying that dx by ds is not a constant. Hey, sorry, I am talking about this particular case. So on that particular edge, your dy by ds is equal to 0. So on this edge, I don't need to enforce this particular condition that f of y should be equal to this one here. But if you take the other edge, right, then the dy by ds is varying, and then you need that this f of y should be equal to this one. So if you see this particular choice that I have made, then you will see that along x equal to plus minus a by 2, this is automatically satisfied. So you will see that so let me just so if you see this, then you will see that since now x square minus a square by 4 is equal to 0, so hence this equation will be satisfied. So let us call this as A, and this equation let us call it as B. So since x square minus a square by 4 is equal to 0, so A is automatically satisfied. It's automatically satisfied by this particular choice, right? So you can see that f of y is equal to this is satisfied on this particular edge, and on the other edge you have that dy by ds is equal to 0. So along y equal to plus minus b by 2. So along y equal to plus minus b by 2, we have that dy equal to 0. Correct? So you can see that see, this is something that I have mentioned in the last class. This condition is to be satisfied as a combination. So that means either this can be 0 or this can be 0. So what we are doing is that now on this particular edge we have dy by dx is equal to 0. So we don't need to satisfy that f of I should be equal to this half of e kappa x square. But on these edges where x is equal to plus minus a by 2, we are satisfying this. So you will see now that with this particular choice, this whole condition is satisfied on the entire boundary. So that is important. Not that individually they need not be 0, but as a combination they need to be 0. And so this particular choice will satisfy that condition here. Okay, so now if you substitute all of that into the del square phi equation, then you will get that del square phi is equal to nu divided by 1 plus nu times p y divided by I y y. So that is the governing equation for phi. And the boundary condition is that phi should be equal to 0 on C. So that is the boundary condition here. So we need to solve this particular equation. So as we saw in the case of the torsion problem, the solution has to be in the form of an infinite series here. So let us write this particular infinite series. So we will assume now phi to be equal to summation of m equal to 1 to infinity, summation of n is equal to 1 to infinity of amn times cos of 2m minus 1 pi of x divided by a times sine of 2n pi y divided by b. See, what is the motivation in choosing this? So first of all, you will see that if you substitute x equal to a by 2, then you will get phi equal to 0, correct? Plus minus a by 2. Similarly, if you substitute y equal to plus minus b by 2, you will get that phi is equal to 0. So that is what we want. We want phi to be 0 on the entire boundary. Not only that, it also satisfies the correct symmetry conditions, right? So now in this particular case, you want your tau yz to be 0 along this particular axis, right? So that is one of the symmetry conditions. So only when you take this particular form, so you know, perhaps there are other combinations that are possible which will give phi equal to 0, but this is the only combination that will give you that the tau yz should also be 0 on the symmetry axis here, this particular axis here. So you know, so that is the way we choose this particular value of phi. So now if you substitute this into the governing equation for phi, then what you will get is that substituting it into this particular equation here. So again, let us call it as 1. So substituting into 1, so you substitute this form into 1 now. So what you will get? So substituting into 1, what you will get is that and then after that, basically you will have to use the orthogonality of the sine and the cosine functions. So substituting into 1 and using the orthogonality of the sine and cosine functions of the sine and cosine functions. We will get that amn is equal to minus nu divided by 1 plus nu times p divided by pi raised to 4 times I 4 times minus 1 raised to m plus divided by 2m minus 1 times n times 2m minus 1 square by a square plus 4n square by b square. Okay, so this is the expression that you will get. And if you now substitute this, so basically this AMN now can be substituted into this particular expression, and now you have the complete expression for phi. And from once you get the phi, then the tau xz and the tau yz can be determined. So let us now find out what is the expression for tau xz. So what we will get is that tau xz in this particular case is equal to p divided by 2iy times a by 2 square minus x square plus del phi by del y, and tau yz is equal to minus del phi by del x. Okay, so now you can see that this particular term here, okay, so this is really quite amazing that this particular term is exactly your strength of material solution. So that means this whatever I have written here is what you would get from your VQ by IB formula is exactly this. So if you recall again that if I draw this cross section in this particular way, you get this paraboidal distribution of the shear stress, and it is a maximum at x equal to 0. So that means along this particular line it is a maximum, and then it goes to 0 at the edges. So that is this, again you can see that when x equal to plus minus a by 2, this part goes to 0. So this is exactly your strength of material solution. So basically now what has come out of this whole analysis is that this is like a correction to your strength of material solution. So that is a very nice thing that comes out of this whole analysis here. So let me just write this here. So this del phi by del y and minus del phi by del x is a correction to your strength of material solution. So let me just write that here. So tau xz tilde is equal to del phi by del y, and tau yz tilde is equal to minus del phi by del x is the correction to the strength of material solution, right? So that's and again we will see that actually these terms can be very large when B is large compared to A. Okay, so that same thing whatever we had earlier also. So you know, basically you get more or less the same thing here. So so similar, so let me write that here. So similar to the ellipse case, similar to the ellipse case, you will see that these corrections are very large. Corrections are large when B is much greater than A. So let me again draw that particular case here. So when B is much greater than A, you have a cross section like this, right? So this is your B and this is your A. And so suppose now you are applying a load P in this particular manner, then that tau x tilde and tau yz tilde are very large. And so basically when you have a case like this, your strength of material solution fails, right? And then I mean, so you have to go to the exact solution when you have a case like this. But if you have the other extreme, which is like this now, so that is this P is now small compared to A, then in that particular case actually the strength of material solution is a very good approximation in that case. So so basically you know, because we now have the exact solution, we can judge whether you know, how good these strength of materials approximations are, because we now have the exact solution here. And so from this we see that actually the strength of material solution is a very good approximation in some special cases. So that is the result that has come out of this whole analysis here. But on the other hand, we have to be careful that the strength of material solution can also fail you know, like in this case or in the case of the ellipse where the major axis is very, very large compared to the minor axis. So, so in those cases the strength of material solution can also fail. So, that sort of brings us to the end of this particular course. To just summarize, actually we have more or less tackled only two-dimensional problems and problems of torsion and bending, which are three-dimensional problems. But you know, just I will mention that in a very briefly here. So just like the Flamand problem, right, we have the Boussinesq problem also, where there can be a point load on a half space. So here in this particular case we have considered this load P, and then we saw, so this was a half space, and then, so actually this is a line load, so that means like this on the on this half space here. So this is a problem that we considered, but similarly you can have the 3D analog of that. So that means now there is this half space here, and then you are applying a load P on the top here. So that is like an axisymmetric distribution you will have. But this is now an actual point load, not a line load as in the case of the 2D problem. So these corresponding axisymmetric problems we did not consider in this particular course, but they can also be handled. I mean, similar problems in the 3D case. So you can take a look at the book. And then this kind of solutions are very, very important because they play a very big role in solving contact type problems. You know, so suppose if you have some indenter that is coming in contact with this half space, right, and then you want to find out what is the stress distribution. So these kind of solutions play a very important role when you have contact type problems. Another class of problems that we did not touch upon at all is transient solutions. Okay, so that is also another very, very important topic. So basically in this course we just considered static solutions, but transient solutions also are very important. And you know, so there are different types of waves, you know, dilatational waves, shear waves, and then there are corresponding wave speeds. And so finding transient solutions is orders of magnitude more difficult than trying to solve static problems, okay, because many times you have to do Laplace transform inversions, which are very difficult, and so on and so forth. So the moment you bring in time, it's a very, very large amount of complication that you are bringing in into the solution. But unfortunately, you know, because of time constraints, we cannot consider transient problems in this particular course. But there are problems on, there are courses on structural dynamics from various departments. So maybe you can take a look at some of those courses. So this course, as I said, that will act, you know, as the sort of starting point for numerical approximations, which is the finite element method. So we saw that we are able to solve, you know, these, we are able to find these exact solutions only for certain kinds of geometries, like the rectangular cross section or elliptical cross section. But now suppose if I give you an arbitrarily shaped cross section like this, you know, some random shape, and then now if you have a load P, then now it is not possible to find an exact solution. And so that is where the approximate solutions comes in, and you know, the finite element method is one of the most powerful methods to find such approximate solutions. But all that we will leave for the next semester. So thanks for attending this particular course.